have, you can have, how many ways can we have 3 people here? How many total people do we have? We have 4 people. How many ways can 4 people be ordered here? Hmm? No? No, because these are separate from here, so we don't have a permutation here. We have 3 here and 4 here. How many ways can I configure these 4 people? Rank 1, rank 2, rank 3, this could be rank 1, rank 2, rank 3, rank 4. How many ways can I assign the 4 ranks to these 4 slots? So I have, how many choices do I have here? How many choices do I have here?
3.
How many choices do I have here? 2. And how many choices do I have here? So is this 4 factorial? Okay, so it's 4 factorial. And what's 4 factorial? 24. So that means that there are, so you're saying there are 24 sequences. 24 sequences that include R5 in this position. So that's correct. So it's going to be 4 factorial. It's going to be equal to 24. This is 3 factorial. It's going to be 6. Is that it? So what you're saying to me is that you can only hire rank 4 or rank 5 in the 4th position. Yes? Make sense? You can only hire rank 4 or rank 5 in the 4th position. Because we already said you can't hire rank 3, rank 2, or rank 1. We ruled that out. We showed that. Add these numbers up. What do you got? 30. How many permutations of 5 do we have? 120. What's 30 out of 120? 1/4. So interestingly enough, for position in 5, we had 1/5. Now here, we ended up with 1/4. Is that the probability that we actually already knew about? The probability of being hired as in 4th position is 1 out of 4. Get it? That's what we just showed. That's what we just showed. So therefore, our probability is going to be roughly less than or equal to natural log of n. That's the expectation. So if you have 10 people, what's the log, natural log of 10? We said it was close to what? Close to 3, right? What if we hire 8 people out of 10? What does that tell us? Could it happen? Randomly selected 10 people, we hired 8 times. Could it happen? Yes, it could. Why? If that happens, what are you thinking? No, you're not thinking like that. Think higher level. What's the expectation? What's natural log of 10? I just did it a second ago. I have to look at it again because I forgot what the number was, but the number was very small. It was 3?
No, 3 is 20.
Oh, 20. Okay. So let's say I have 20 people. I expect to hire how many? 3. Let's say I'm hiring 10. What am I suspecting? What's wrong? Is my mathematics wrong? No. Order doesn't appear to be random. It appears that somebody is playing around with the order. They're putting them too much in increasing order, too close. Now, we are not in a position to say that the order is not random. To do that, you need to take a statistics course and have a statistics test and determine whether you can reject the hypothesis that the candidates are in random order. There's a hypothesis testing for that, so it's beyond what we have, but it's not beyond our common sense. If the expected value is 3 and we get 8, then we suspect it's possibly not random. Now, can 8 occur in a random situation? Yes, but with very what? Very low probability, so it's very unlikely. Okay? So if you buy a lottery ticket, what do you expect to have happen? What do you expect when you buy a lottery ticket? You expect to win? You start spending the money before the lottery is drawn? No. So if you buy a lottery ticket, you should expect to lose. Because you're going to lose almost all the time. So if you don't buy a lottery ticket, you're really saving money. Most of the time. 99.99999% of the time you're saving money. 999, keep going with the nines. Okay, so that the idea is, now, I have another problem that I'm not going to cover because we're running out of time, but we'll talk a little bit on Wednesday, and that is we're going to change this and call it an online hiring problem. It becomes more interesting. So, this is a very interesting problem. This is what we call an optimization problem. What we're going to do, and I'll just introduce it very briefly and I'll let you guys go. Basically what we're going to do is, so this is the set of candidates that we're going to hire from. Okay? We're going to assume they're coming in at random. They're N candidates. What I'm going to do is I'm going to come up with a number K, which is much less than N. And I'm going to interview the first K candidates. So interview candidate 1, 2, 3, K. So the remaining candidates are K plus 1 through N. After I interview the K candidates, I'm not going to hire any of them. They're random. I'm not going to hire any of them. I'm not going to tell them that. I'm not going to hire any of them. But what I'm going to do is I'm going to now start interviewing candidates K plus 1 and moving forward. The first candidate I interview, starting with K plus 1, that's better than the top in my K gets hired. And the question is, what is the optimal number of K? How do you choose the best K so that you maximize the probability of hiring the best candidates? Not guaranteed, because this one guarantees. This one guarantees. You're not going to miss the best candidate. But you're going to hire 3 out of 20. I want to hire exactly once. I don't want to fire anybody. So I just want to interview the first K. So let's think about it. If you make K equal to 1, you interview one candidate and you hire the next person that's better than them. Well, if this is the worst person, then you hire anybody who's better. If you hire a rank out of 10, rank 3, then you hire rank 4. Now, if you increase K out of 10 to 3, and you interview the first 3, you get the idea how good they are, and hire the 4th, what's going to happen? How likely are you to hire the best person? How likely is it the best person will be in the 4th position, or in general, in the K plus 1 position? Okay, we'll come back to that on Wednesday. All right.